This is the friction video. So the original question was, how much force would it take to get Bob, this anvil, to start sliding? So if you answer that question, it weighs 250 newtons. Obviously, that's a force going down. So would it take more than 250 newtons, equal to 250 newtons, or less than 250 newtons to get this anvil to start sliding on the table? I'll give you a hint. What are you pushing against? Are you pushing against its weight, or are you pushing against its mass? Or is there something else resisting the motion? So we do have a force. We got what is resisting that applied force that you are pushing? So it's friction. Right, so friction plays such a big role in our lives that it is important that we have some knowledge about it. So the old adage is know thy enemy. Well, turns out that friction isn't always the enemy. So here are some advantages of friction. So every day you interact with a frictional force and you don't realize some of the advantages. Without friction, we couldn't like get a car moving, turn a car, stop a car, run around, keep your pants on, even with the belt. Even just walking from place to place. A frictionless world would not be a good place to live in. Now, there are some disadvantages to friction. So because of friction, like our joints wear out over time. And you can trust anyone like over the age of 30 on this one. So do brake pads and tires. Cars will overheat without enough oil. Gas mileage goes down because of friction against the air. Friction is both necessary but also has a lot of disadvantages. So friction is a force that always acts in a direction to prevent sliding action. If no attempt is made to move the object, then no friction acts. So if we zoom in, right, if we look at friction a little closer and understand exactly what causes friction on like a macroscopic level, friction arises from surface irregularities. So you can see here that all surfaces, even smooth ones, have little bumps that are going to bump into each other and hook onto each other as they're sliding across each other. Now, on a microscopic, so on the atomic level, we understand that friction is arising from intermolecular forces of attraction between neighboring atoms of one surface to the other. So just what you need to know is that friction is just basically just those surface irregularities. So what affects friction? Two things affect friction: the nature and condition of surfaces and how hard the surfaces are pressed together, or also known as that normal force. So you can see here the normal force. Well, if you have a larger normal force, is pressing those surfaces together harder, or it also depends on, well, what surfaces are being slid together. So there are two types of friction. Static friction is the friction force that resists forces being applied to the object attempting to slide the object. The surfaces between the objects will not slide until the static friction is overcome. Now, static friction will equal the force attempting to slide the object until static friction is overcome in magnitude, but opposite in direction. If static friction is being applied to an object, that does not necessarily mean that object is at rest. So an example would be walking around. So kinetic friction is defined as a force that acts on an object as it is sliding between sliding surfaces. Now, kinetic friction does not depend on the force attempting to slide the object. So if you look at that, the little graphic up here, notice that the applied force, you can see the applied force is getting larger and larger. Well, you haven't overcome that static friction yet. So if we look at that smaller arrow, notice it's getting larger and larger, and it's matching that static friction in magnitude, but in opposite direction. Now, there does reach a point at which those two surfaces, those conditions, cannot hold it in place anymore. Once it does, well, it's going to overcome that static friction and it will be sliding, and then you have kinetic friction. So static versus kinetic friction. So static friction is almost always more than kinetic friction. There is a rare occasion where static and kinetic friction are equal, like in the case of Teflon on Teflon. Kinetic friction will never be greater than static friction. Now, what this means is that it is harder to start something sliding than it is to keep an object sliding. So if we watch this video, we'll see that it takes about 20 newtons to get this object to start sliding, and once it is sliding, it takes about 16 newtons to keep it sliding. So notice it's pulling, and then at 20 newtons, it starts to slide, and then it takes about 16 newtons to keep it sliding, because it's harder to get an object to start sliding than it is to keep it sliding. So these are the equations for friction. Now, there are two equations. One is for an objects that are not sliding, so that'd be static. And one is for objects that are sliding, and that'd be kinetic. So that frictional force equals the coefficient of friction times the normal force. Now, the lowercase Greek letter mu represents the nature and condition of surfaces. You'll usually look this up in a table. You can see this table right here. You'd have the coefficient of static and coefficient of kinetic friction. Notice that the coefficient of kinetic friction is almost always lower than the static friction, except in the rare case of Teflon on Teflon, in which they're the same. Now, the normal force represents how hard the surfaces are pressed together. And I always joke around and say, if you ever need help remembering the equation for friction, remember that friction is fun, right? So just a little joke there. Okay, so things that do not affect friction. Surface area of contact does not affect the amount of friction being applied to an object. So if we take a look at these videos, notice that the person is going to be pulling this block, and it's on its side, it's horizontal. Then the next slide, they place it vertically. But notice this person has the same amount of weight on it. So the normal force is the same, nature and condition of surfaces are the same. Those are the only two things. So let's take a look. So it takes about 12 newtons to slide it when it's horizontal. Let's take a look at it vertically. Takes about 12 newtons to slide it. So notice the nature and condition of surfaces, notice that the surface area does not affect that friction. Now, the relative speeds between those surfaces do not affect friction. So let's just take a look at this video clip, and you'll see this person has a belt sander, and they increase it, and once it gets settled, you'll be able to see that the friction is going to be about the same, whether they speed it up or slow it down, right? So you'll see that they'll speed it up, lower it, speed it up, lower it, but notice it's still, that frictional force is still the same. That frictional force is still the same. All right, so if we look at a graph, notice how the object is not, notice that when the object is not sliding, the static friction will equal the applied force. So that's this red bar right here. So the static friction will equal that applied force. There is a limit to how much static friction two surfaces can provide. That's that point right there. Once that point is reached, the object starts to slide. That's what this equation gives us, that maximum static friction. Now, when the object is sliding on the surface, then kinetic friction can only provide so much. The equation for kinetic friction will give you the amount of friction those surfaces can provide while the object is sliding. You can see here that it doesn't matter how hard you push. If it's sliding, it's still going to be this. It's still going to be that equation. So if we zoom in a little further, you can see that if no attempt is made to slide this object, there is no frictional force. Now, if I move up a little bit, I have an applied force, but I have not overcome the static friction, so I still have a small frictional force. Now, notice as I move up, I still haven't overcome that static friction, so my frictional force will match my applied force. It isn't until this point in which I calculate this maximum amount of static friction. If I do not provide more than that, it will not slide. Now, kinetic friction, it can only be so much. It does not matter how much, it does not matter how hard you push or even not pushing. If those objects are sliding, or if that object is sliding, it can only provide so much of a static friction. So let's take a look at some problems that we can have, right? So on this one, a box of 50 kilograms is being pushed on a level surface with a horizontally applied force. It just starts to slide when 60 newtons is applied and will continue to slide if 45 newtons is applied. So the first thing we need to do is figure out how hard those objects are being pressed together. So that's going to be, well, the weight. Now remember, weight is going to be a negative force because it's pulling down. Now the normal force in this case is going to balance it out at 500 newtons. Now, I need to find the coefficient of static friction. So I'm going to use that first equation, and I plug everything that I know in. Well, it just starts to slide when 60 newtons is a push, so that tells me that's the maximum amount of static friction. I know it weighs 500 newtons, and I just solve for the coefficient of static friction. I do the same thing with that second one. So I know it's going to continue to slide if 45 newtons is applied, and it has the same normal force. I plug everything in, and I get the coefficient of kinetic friction is 0.090. Now, this is the graph that you have. Notice that the static friction is going to match the applied force until you overcome that point, that maximum amount, that 60 newtons. Now, you can also have a question like this. A box with a mass of 60 kilograms is being pushed on a level surface with a horizontally applied force. The coefficient of static friction is 0.100, and the coefficient of kinetic friction is 0.080. So we need to find that normal force. It's 600 newtons. So there's the gravitational force. Yeah, it's going to be down, but the normal force balances it out at 600 newtons. Now I need to find the max amount of static friction. So all I do is I multiply the coefficient of static friction times the normal force, 50 newtons. Then I need to find the kinetic friction. I just multiply those two together, coefficient of kinetic friction by the normal force, and I get 40 newtons. And when I graph it, I get something that looks like this. So I get 50 newtons. So I get, 50 newtons, and then there's that 40 newtons kinetic friction. All right. So now the next one is a known graph. So you can see here I have a graph, right? A box with a mass of 25 kilograms being pushed on a level surface with a horizontally applied force. So now I know that the normal force is going to be, 25 times 10, which is going to be 250 newtons. Now I also need to find the maximum amount of static friction. If I look at the graph, it's 90 newtons. So I just plug that in to find the coefficient of static friction. And if I look at that graph again, I can do the same thing for kinetic friction. So notice the kinetic friction is 75 newtons. Then I can find the coefficient of kinetic friction. Now the last one is a chart looking up the coefficients on that chart. So a wood box with a mass of 12 kilograms being pushed on a level wood surface with a horizontally applied force. What is the weight of that box? What is the normal force? Sorry. It's going to be 12 newtons. And now I have to look this up. So the coefficient of static friction is 0.5, and the coefficient of kinetic friction is 0.3. I can look that up. And then once you do that, you can calculate the maximum amount of static friction and that kinetic friction and then graph it. So that's what it's going to look like. So in order to reinforce all of this, we did that friction simulation. We calculated the weight of the box, the applied force applied to that box. So that one's just pushing the box until it starts to slide. Now, these questions you can answer. As the box is sliding, what kind of friction is resisting the sliding motion? It's going to be static friction. And what is the force being applied to the box as it's sliding? That is going to be kinetic friction. Now we can calculate the coefficient of static friction and kinetic friction based on these equations. If you know the maximum amount right before it slides and the frictional force as it's sliding. Yeah. Okay. And then you can graph this. So right there, once again, that is the maximum amount and that kinetic friction, that is as it's sliding. So you can have free body diagrams for several different scenarios. We just kind of skipped over that section. Now, when we turn the friction all the way up, what happened to the normal force? Nothing, right? Just because what I'm doing is I'm changing the nature and condition of surfaces. Now, the applied force is going to take a lot more of a force because, like I said, you're changing the nature and condition of those surfaces. Now, the applied force is going to affect that static friction. If I do not overcome that static friction, my static friction will be the applied force right back. So if I push with 10 newtons, static friction is 10 newtons right back. If I push with 20 newtons, 20 newtons right back. Now, the kinetic friction does not matter, or is not affected by the applied force. So let's go over some practical things as you're driving, how to take advantage of friction. How can you use your knowledge of friction to survive when your car goes into a skid? So that's anti-lock brakes. So if you look at this symbol, it's anti-lock brakes. Anti-lock brake system uses the difference between static and kinetic friction to come to a stop quicker. Now, how does it do this? So if we look at this, if your tires begin to slide, anti-lock brakes release pulse the brakes to apply static friction repeatedly. So without anti-lock brakes, the tires are sliding on the ground, and kinetic friction is being applied to the tire to stop your car, which is not as much as static friction. So what it does is it lets your tires roll a little bit, and then it stops it again. So it's applying that static friction over and over again as opposed to just a kinetic friction. So it takes advantage of that. So if your tires begin to slide, anti-lock brakes release the pulse brakes to apply static friction repeatedly, turn into the skid. That way, when that static friction kicks in, the tires will be facing the direction you want to be going. So you always want to, like if your back end starts to turn to the left, you want to turn your tire to the left. And as you can see here, if you're turning, like on a turn, this is counterintuitive. So this person, they're in the skid, they're turning towards the back end of the car, but it is in the opposite direction of the turn. So it can get a little scary there, but that's what you have to do in order to get those tires facing the right direction when that static friction kicks in. So we did do this lab, the hands-on friction lab. So we did the resolution. The first thing we need to do is find the weight of that metal cylinder when we're pulling that box. So we know that it's going to be, let's see, it says 0.6 kilograms. That means it's going to be 6 newtons. Now the box should start at rest with the spring scale. What you're doing is you're pulling this box until it just starts to slide. So if I pull with 1 newton, it's gonna frictional force will be right back with 1 newton. So you keep doing this until it just starts to slide. So you should see that. Then you're going to calculate the coefficient of static friction and coefficient of kinetic friction. Then you're going to graph. Now, when you're just doing something small like this, like a 12 Newton object, I think on this it was like the max amount of static friction was like 4 or 5 newtons, and then as it's sliding, it was like 2 or 3 newtons to kinetic friction. Then we drew 3 body diagrams of different ones. Now, let's just answer this question. What would happen to the applied force required to start the box sliding if another half a kilogram cylinder was put in that box? What variable does this change? So this doesn't change the nature and condition of surfaces. What this does change is that normal force, how hard those objects are pressed together. Does the applied force affect the static friction or the kinetic friction being applied to the box? The applied force affects the static friction, because remember, kinetic friction does not depend on the applied force. Now, this last question, the moon has 1/60 the amount of Earth's gravity. Imagine this exact experiment were to be performed on the moon with the same table, same box, same metal cylinder, and same spring scale. Would the results of this lab change? Why or why not? The answer is yes, it would change, because you wouldn't change the nature and condition of surfaces by going to the moon, but what you would change is how hard those surfaces are pressed together. Now, we did the meter stick friction lab. So you can see here, what you're doing is you're putting the fingers on the ruler at the designated points and slowly moving your fingers towards the center, and you mark where your fingers result in that graph. So these are the answers that I got. They always meet in the middle. So how did the original placement of fingers of the ruler affect where they met? They didn't. It didn't. They always met in the middle. Now, friction depends on only 2 factors, the nature and condition of surfaces and how hard those surfaces are pressed together. As your fingers move towards each other, which variable does this affect? So this isn't going to affect the nature and condition of surfaces, because that's like dependent on your finger and the wooden meter stick. But what this does do is it does change how hard those surfaces are pressed together. The closer your fingers get to the center, it's pressing those surfaces harder together. Now, if you move your fingers slow enough, only one finger moves at a time. And what happens is because, well, you have a static friction on one as it's not moving, and then one of those fingers is sliding. And then once that kinetic friction on one finger is greater than the static friction on the other finger, that's when it switches, and it goes back and forth until you meet in the middle. So just kind of a little thing, and this works with all long objects that you can hold on your hands. That's how you can find the center of gravity. So what type of friction allows you to walk across the room? It's going to be static friction, right? It's responsible for you being able to walk. You have an issue if your foot is sliding, right? You are probably on ice. And you can see here, you do not want your foot sliding. So I'm applying a force on that road. Is that frictional force is what's going to push me forward. Could you run faster on a planet with less gravity? So we also learned that friction depends on nature and condition of surfaces. It would affect if you were to go to the moon, that would affect how hard those surfaces are pressed together. Friction would change on another planet. Now, there are other factors at play when we're talking about running in low gravity. So that means like you do have an upward motion. There is a lot that goes into this, but yeah, it would affect the amount of friction. What is the best strategy for taking advantage of the nature of friction when playing the game Jenga? So we did this lab in which we were playing Jenga, and we're going to use our knowledge of Jenga to take advantage of it. So let's just take a look at these. Which friction provides a lesser force, static or kinetic? Well, it's going to be static friction. If someone repeatedly taps that Jenga piece, what type of friction are they applying? Well, it's going to be that if somebody is repeatedly tapping a Jenga piece to get it started over and over again, that person is applying a static friction force repeatedly, just like anti-lock brakes. Now, if someone gets a Jenga piece to move, then keeps that piece sliding, what type of friction are they applying? It's going to be kinetic friction. Now, you would want to apply kinetic friction. You want to keep that object moving because kinetic friction, as you can see down here, is less than static friction. So that person tapping over and over again, that's going to apply a static friction, and that's going to be larger than kinetic friction. Yeah, by keeping the block sliding once it starts to move. Now, would you want the block to pull out quickly or slowly? Does friction depend on relative speed between surfaces? It does not depend on the relative speeds. However, which you want to remove it quickly because you want to apply that frictional force to the big tower for the shortest amount of time possible. So the best strategy for playing Jenga is to remove the block one motion quickly to take advantage of the fact that kinetic friction is lower than kinetic friction, and removing it quickly to reduce the time the kinetic friction is applied. So that basically is all of these questions right here on that lab. So once again, as a final thought, there's too much unknown in the universe to take a break from learning. Get out there and question everything.